Hi! It's machine learning time. And today is actually a really good one. I'm very excited about this one because today we're getting to neural networks. But not yet. We need to recap, make sure everyone's on board with where we're at. So, how are people feeling? Just going to gauge the room real quick. Thumbs up or thumbs down? How are you feeling about the stuff we've covered so far? Okay. And again, a good amount of thumbs up. That's good. That's good. A good amount of no thumbs, which is probably a thumbs down. So here is where we started. Was we had some data, and we have an x and a y axis in this case, and we want to find some line that fits it. We want to find some line that represents what this data is. What we realized is that when the data isn't precisely on a line, we can end up with multiple lines that could all be described as good fits. And we don't really have any way to say which one's better or not before we introduce the next concept, which is a loss function. So we said, maybe we measure how good this is based off of the distance it is from each point. So it has essentially a prediction along this entire line. And we want to see at these data points, how close is it? And we established the idea of a loss function, which is how poorly it does. Bit of a weird wording, but that's what we do for machine learning. And this was this particular case was just the absolute distance from the line. It was the most basic, most obvious thing that we could do. But we realized that there could be multiple different loss functions that we could use. And this loss function is, so in general, minimizing the loss function will be improving accuracy because that's how we define it. That's how we define what loss is. We also realized that because of this, if we were to use a different loss function, then we are optimizing different things. In particular, we talked about mean squared error, which is just the distance squared, and how that one cared more about points that were very far away because we're squaring them. Then we talked about how we actually go about minimizing that loss. And we talked about gradients. So the gradient of some function at some point is going to be the direction of steepest ascent. Just to remind you, that's a very important thing to remember. And not that necessarily it's ascent, but it's important to remember what a gradient is. And then, as a corollary, the direction of steepest descent is the negative gradient. And since we are looking at this function right here is supposed to be our loss function with respect to all of our parameters. Hopefully you guys remember what parameters are and you feel really good about that. Essentially, our model is going to be some parametric function, and based off of those parameters, we will have some loss. And we want to reduce that. So we're able to take steps in the negative gradient. So we can change our parameters the same as moving the direction of the negative gradient. And we get a nice little equation for that. Is going to be this. And this is our first step towards stochastic gradient descent, machine learning, and all the things that we actually care about. There is a problem with this, though, with this formula. I mean, it's intuitive. We're moving in the negative gradient. Negative gradient will decrease loss. We know that as long as we take a small enough step. And that is the key there, is that you can imagine a situation like the one that I showed you last class, where we have some loss at some point, and we could take a step in the negative gradient, and maybe we move this far. And that places itself nicely right at the minima. Great. But the gradient does have a magnitude that is based off of both the input and other properties of our model and our task. So it could be that we have a higher magnitude gradient, which means instead we take a jump farther and over the minima. In fact, in this case, we can see that we are increasing loss. We don't want to do that. So we introduce some way to control how big of a step we're taking. And we call this the learning rate. So we use LR. Some people use a little rho symbol to mean learning rate, but we are going to say LR because what's the point? And this is just a scale on how big of a step we're taking. So if this learning rate is small enough, this is a theorem that I handed to you. If this learning rate is small enough, we will necessarily decrease loss every single time we update our weights like this. It's a very nice theorem to have to start on the basis of what we do with machine learning. Anyway, The other thing that we talked about, which we didn't have as much time for as I would have liked, but I'm going to reintroduce it a little bit, but sort of hope that you guys got the idea of it, which is computation graphs. So we have this function right here, y equals x plus 4 squared plus 1 to the 8th. And I said that we cared about finding the derivative of this function with respect to x. And the way that we went about doing this, instead of just using our calculus, was to draw a computation graph. So every operation that's happening in this, we draw as a little purple square. And we go through the whole thing, and then we realize that we can calculate the partial derivative of any function by going backwards and finding the path from the first variable to the second variable. In this case, go from y to x, and we go through every single one of these and calculate the partial derivative in each step. So it looks something like this. And we know from chain rule that this will resolve to be dy over dx. So that's a very nice idea, and this is in fact how our program will find the gradient for the functions that we care about. So it's important to have this idea, and it will also help you later on to realize how generalizable a lot of the ideas we're talking about are. Neural networks and these sorts of standard machine learning practices use particular functions, but you don't have to. You could use any sort of function and still do gradient descent. And I think that's a little bit of a mind-opening moment once you start learning a bit more about machine learning. Anyway, so that's the recap. Now we're on to some new stuff. So first up, we've had all of these one input, one output examples, but that's a very small class of problems that we have in the world. So I'm going to give you a little bit of a harder example. So this was our example before. We had the inputs, which were hours of sleep, and the labels, which were the scores on the final. But what if we introduce another input variable? Each student will now have a number of hours they slept and a number of hours they studied. We're going to plot this still as a 2D graph, and we're going to do it like this, where the two inputs are going to be each of the axes, the y and x axis. I'm not going to draw a z-axis, because that is a real pain to do in Google Slides. So instead, I'm going to have each of these points, and I'm going to label each of those points with their value. This is a lot less visual. That's why we started with the 1D example. But if you want to try to visualize what's going on here, imagine we did, in fact, have a 3D space. And now, instead of finding a line to correlate to all of them, we're finding a plane. And essentially, as we raise into higher dimensions, we do that, and we raise the dimensions, and visualization completely goes out the window, but we do have some semblance of it here. Anyway, so we know that then once our model is trained, or before our model is trained, using its parameters, we will be able to take both of those inputs, and we will produce some score. So every single point on this entire plane will have some value. And that is going to correspond to our model. A lot of people visualize this as a gradient, not as a gradient, that's a bad word to use, they do call it that, but as a vector field essentially. So you have a different heat on each value, and then you can see and visualize it, and you can see what your model has learned, instead of doing a plane, because the planes don't really visualize well. Anyway, so I want you to think about how this would change our loss function. So to remind you, we had this notation before where our MSE is going to be the average of the summed square difference of every single point. So this yn here would be the nth data point. It would be one of these data points compared to what the model predicted at that same point. So how would this change our loss function? Yeah. We just need more dimensions for it. This is the shorthand answer is it really doesn't. So we're going to now have for each of these, we'll have a y that has we'll have an x that has one dimension. So in this we'll have two possible dimensions, and we'll compare them. Actually, in this case, it doesn't change it at all. Later on, it will change it more, actually, when we have multiple outputs. So it actually doesn't change it here at all because the inputs don't actually affect the size of the output. Sorry about that. But it does get the point across that no matter what, no matter how many outputs we have, no matter how many inputs we have, we can still use these same fundamental loss functions because we can formulate them as vectors, which I know a lot of people are going to hate at first and eventually learn to love the idea that I keep talking about vectors and matrices. We'll get to it. All right. So This gives us the concept of multidimensional data. So before, we had just all the inputs labeled by which input they were. And now we're introducing the idea that all the inputs could have multiple dimensions. So instead, we're going to have, for any xq, so any qth data point, we will have 1 through d, in this case, features. We're going to use that word a few times, try to remember what it means, features, that are going to correspond to all of the different attributes of our input, or all of the different dimensions, if you'd like. So this is for some n-dimensional input, or so d-dimensional input of n inputs. So you can see why, you're probably getting an idea of why I use this weird notation. We have a lot of this going on. And then we can update our picture. So before we just had an xq going through our model and getting a yq. Now we're going to have multiple x's going in and one y coming out. Yeah?
Just to clarify, so the single input, is that like a single instance of one of the all inputs? Or could you just clarify on that?
Yeah, so he's asking whether this is one instance of the whole input array, I assume you mean. So yes, it is. So essentially, we now have a two-dimensional matrix as an input, sort of. We're going to go over a little bit later how that interacts with what we're doing. But essentially, this is a list of inputs, and each of these is a list of attributes or features. But the story doesn't stop there for our generalizing to what we can do. We can actually introduce features into our outputs, which I was hinting at earlier a bit incorrectly. Here, we will now have c dimensions on each of our outputs. So we could have, let's say in the case of our example, we could have hours of sleep and hours of study turning into score on the final and score on the midterm. We'd have both. We'd have whether they like cats or dogs on there too. We could have whatever we want as the output. So that's an important note, is that we can have any amount of inputs to any amount of outputs. Again, machine learning can become very, very general. So this is the sort of power of it. And we're going to update our picture again, and now we're going to have something that looks like this. Slowly, 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 this picture is going to turn more and more into something that might not look familiar, but is much more contemporary. Anyway, so this is the general form of a machine learning model using supervised learning. Cool. So let's talk about something a little bit different. We have all of this now. We have a model that can do this. Cool. But what if we have this data, right? We have the same inputs, but now as an output, instead of having the score on a final, we have a Boolean. We have whether or not they passed the class. So let's plot it. So we see on here, and we have a bunch of yeses and nos. And what do we want to learn? What would be useful here? Yeah?
Maybe a threshold on the graph of where if you could fall on one side or the other side of the threshold, then you'll either be a yes or a no?
Pretty much precisely. I'll make it a little bit more specific. We would like, because we're doing linear models right now, we would like a line that separates the two classes. So this task now is a little bit different. And you might notice that we can't use the exact same tools we did before. Before, we were trying to get really close to the points. So what do we do now? This task right here is called binary classification. It's a subset of classification, binary as in having two classes. Pretty straightforward. So I want you, now this is you talking in small groups, think about the ways in which this is different than regression. What is different now for us in terms of wanting to do machine learning? All right, go, talk in your groups. All right, all right. So, how are these different? I mean, they're pretty obviously different, but how are they different for us? In terms of all the things we have, in terms of model, in terms of loss, in terms of anything else that you want to talk about. I'm going to wait a second, see if anyone else. You as well. I want to hear from people who are maybe not as necessarily confident. Yeah.
Is it maybe like a difference between something continuous and something discrete?
Good eye. I said that in the initial quiz, and that is absolutely true. Right now, instead of outputting some continuous value like we did with regression, we have just some number. Now all of a sudden we have a class. We have a 0 or a 1, a yes or a no. How are we supposed to do approximation on that? How are we supposed to get closer to 1 and 0? Yeah?
So for linear regression, we kind of compute the loss by calculating by minimize the distance.
Mm-hmm.
But for the classification, we could check the result is true or not, and then we know the error we make.
Basically, yes. So one change that we're going to make, and this is going to be an implicit change. I'm not going to talk about it explicitly because I think it might catch people a little bit. But essentially, we're going to be able to do more or less exactly the same thing. Weird. But what we're going to do is we're only going to update when it's incorrect. So as we go through the data points, if it's wrong about some data point, we'll move it so that it's closer to right or right. And essentially, if we iteratively do that, then we will eventually get a line that should separate them correctly. One other difference that might be notable here is the fact that with linear regression and some loss function, we would have some particular best setting, generally, or multiple best settings. But with classification, you could imagine tasks where there is an infinite set of optimal solutions. As long as we have a line that separates them, it works. So now, we've talked about how we have to change our problem in some way. We have to make some threshold. We have to change the way that we're learning a little bit. But how exactly are we going to do that? Yeah?
So maybe we could just do like a linear regression, and then maybe on the output we can like model something from the output that we get from that model.
Model something from the output. I'm not sure what you mean by that.
So like from the hours of sleep and hours of study we get the number of marks, right?
Mm-hmm.
And then on that number of marks we study if they're passed or not.
Okay, so essentially doing linear regression and then correlating those outputs of the linear regression to something else. That is a domain of machine learning called transfer learning. Problem being, lots of times we don't have any other values, and if we want to create some synthetic value, then essentially we might as well treat this as just being ones and zeros and just doing linear regression on it. It's exactly the same thing. But not a bad idea. It's a better idea when we are talking about more complicated models. Right now, it doesn't really work that well, actually. And there is a very simple, satisfying answer for how we can actually do this. So we are now doing the task of classification. You might have been able to pick up on that with the way that we're doing classes and saying which class it's in. So essentially, we have this right now where we want to separate the different classes. And this is our model. I'm going to point out that I'm using the matrix multiplication notation here. This is exactly the same as saying W1 times X1 plus W2 times X2 plus B. It's exactly the same thing, but now I'm using this matrix notation. So this is where W is equal to weight 1, weight 2. And that little T is transpose. It's something that, for whatever reason, I didn't know until I was a grad student, actually. Funny. Transpose is just taking a matrix and swapping its dimensions. The reason it's important to do it here is that our weights are essentially an array, and our inputs are also an array. And if we want to do matrix multiplication on them, we need to change them so that the dimensions match, and we can multiply each value with each other. If you don't understand any of that, that's also fine, because linear algebra is not a requirement for this class. But I really recommend you look up some linear algebra, see how matrix multiplication works, and it should make total sense. For the most part, you don't actually need to understand how matrix multiplication works to do any of this. You're going to just have to trust me. All right. So how might we do it so that we actually have this boundary? So that's our function of the line. Cool. And let's say, I'm just going to give you this. Let's treat all of the yeses as 1 and all the nos as 0. If this is our trained line and those are the parameters, how could we actually get it so that all of the yeses are 1s and all the nos are 0? What modification could we make? Yeah.
You can round the answers off.
Round the answers off. So round them to the nearest integer or nearest 0 or 1. So the idea there is actually pretty close to something that we'll touch on later, which is called a sigmoid. We're not going to do that for the sake of doing something a little bit more simple. Also, sigmoids suck, so not that it's a bad idea, but it just does happens to not work well. But yeah, people had that idea. Not quite, though. Let's do something even simpler. How do we turn some value into a Boolean? Imagine you're programming, and you have some number, and you're turning it into a Boolean. What sort of thing might you do?
Compare it with 0 or 1. Like
Compare it with 0 or 1. So like less than, equal to, or something like that?
yeah, or like with the or and operations.
Cool. Yeah. So what we're going to do is a very small modification, and it will work. All we have to do is say if that is greater than 0. That's it. Now, the reason that this is so good, so one, when we're actually doing back propagation, you remember gradient descent, all that? That's still happening. When we do that, our loss will be 0 or 1. Or I guess it will be -2 or 0 or +2. And when they're equal, it will be 0 with this function right here, which means that we don't update if it's wrong. And if it is wrong, then we have a very simple way to update it. We move it based off of just the gradient. We just move it scale times the gradient. And that gradient is very simple. You'll see it in the homework. But this really does work. And the beauty here, the sort of simplicity here is if we had a model that did regression with these same values, and then we just added this thing, it wouldn't work. But because we're learning these parameters, if we set up our function like this is essentially the same exact thing as changing the loss function. It's either changing the model or changing the loss function. They're kind of one and the same in a weird way. And when we go do gradient descent, the machine learning does its magic. Gradient descent works. It's really great. And in fact, this actually ends up being able to separate any linearly separable set of points, which is really cool. So if there are two classes where there could be a line that could separate them, and we made this our model, just greater than 0, and we did gradient descent, it will find the correct answer, which is really cool. I know that we had that for regression, that it would find an optimal, but the fact that it does it for classification too is another beautiful result. Cool. So it would look something like this, where it has these regions that are 1 and 0, and essentially that's all we want to do is we want to change this regression to classification, and we can do it just with a Boolean operation, like greater than or less than. Cool. By the way, this would also work if we changed it to less than. It would be able to learn it just as well, which is weird. Anyway, so remember how I said there were going to be quizzes in the class? Today's one of those days. So could someone from one of the groups just come up here and grab quizzes for everyone? Here, you got it. Yeah, 1 second. Yeah. Cool. Cool. Oh, there's one, whatever. He'll live. Yeah, wait. Does your table not have one already? I think he just grabbed one, didn't he?
Over there.
Okay. Could I have, here. I think we might be missing a couple. I don't know how many there are in each one. There's either 8 or 9 in each stack, I think.
Yeah, I got enough.
What? You have enough? Oh, so you did already grab it. Okay,
No,
okay.
I didn't, but
Okay.
But it's fine if you want to.
You can have an extra one if you want. Oh yeah, go for it. Anyone have one more? Any group have one more? Yeah. Yeah?
How much group work is allowed for
None for now. All right. Still need two? Need two more. Who's got them? Two extras? I printed out enough. Okay, there we go. All right, here you go. Does that mean did everyone show up to, okay, cool. One person skipped. Cool. I can live with that. All right, so, okay, I guess no one skipped. All right, cool. Well, thank you all for showing up. So, you all are going to get 15 minutes on your own to work on this. I'm going to warn you that this might be a little bit hard. That's sort of the point. Like I said earlier, challenging but not overwhelming. This is a little bit of a challenging quiz. If you get them all, good for you. If you can't get them all, don't worry about it too much, okay? So go, 15 minutes. Hey everyone, just jumping in to clarify something that I bet a few people are not 100% on. So on question 2, I say that I want low proportional difference for each one of these. That means that a difference of 0.0001 and 0.0002 should be weighted the same amount as 1,000 and 2,000. That difference should not be absolute difference, it should be proportional difference. Make sense? Hi, everyone. Again, quick clarification. So on the computation graph question, which, by the way, is meant to be an extremely difficult question. You're not wrong about it being hard. We say that x is a vector with two values, and then later on I have it being subtracting something from it. The way that subtraction and division and all of those other basic operations will work, unless I specify otherwise, is element-wise. So if I had x minus 3, that means that the output would be x1 minus 3, x2 minus 3. Same with divide. Cool. I'll point this out in case anyone else is making that reasonable mistake, is that x, when I say that x is x1, x2, that is one data point has two features, not two data points. That's why the notation matters. Again, it's very complicated, but once you get used to it, it's not that bad. All right, so that's time. I expect most of you to think that that's horrendous. Also, don't hand it in if you're getting ready to do that. It is, and I'd like to clarify my intention with this class. I never want to have anything trivial or boring. I would much more err on the side of interesting and perhaps too difficult. So it is intentionally difficult, but it's supposed to show you particular things. All right? And you'll see how it might not be that bad. All right, so next up, I want you to pair up with a person or two people and talk through your answers with them. All right, go. You want to pair up with the UCA? You want to pair up with the UCA over on the other side? Oh, I was just asking if you want to pair up. So the UCA over there is like the UCA for the guy. You can talk to him. He's probably had trouble with the problems too, so it's not like. Okay, so there's no chairs. That's crazy. Oh, is someone actually sitting there? One second. Yo, is anyone sitting here? Oh yeah, no, we have exactly enough chairs for everyone, so we have to, yeah. All right, all right, all right, all right. Do I need to be louder? All right. Hey, that one worked. So that's the end of the pairing up thing. Don't stress about it too much. And if you changed your answers after you talk to other people, that's fine. That's actually what's intended. So now let's go over the answers, and you can see how you felt. So number 1, a model which predicts the following way: y equals w1x plus w2x squared plus b, with x as an input and those as parameters, can be used to do linear regression. How many people said true? How many people said false? Congratulations, minority. So this is in fact false. The reason being, the very simple reason being, the model isn't linear. Linear regression is exactly when we are fitting a line. Pick some parameters and plot this, and you'll see it isn't a line. It's a parabola. That's not actually linear regression, but it does give you a little hint at the fact that we can do other types of regression, other types of classifications, by changing our model in interesting ways. This is actually called a basis function. This is a polynomial basis on a linear regression, is what it's called. It's not linear regression, don't worry, but there is some interesting ideas of how we get nonlinear stuff out of doing something very similar to linear regression. Anyway, second, it is possible for two identical models, trained on the same data, but using different loss functions, to find the same optimal parameter values. True? False? Dissenters? You won last time. Just a couple. All right, it is true. So there's a lot of different ways that this could go. The very easiest you can imagine is, here is an example. We have one loss function that is just the square difference, and one that is a square difference plus 5. There's no actual difference. There's no dependence on this that's actually changed. These loss functions are definitely different, and they definitely would have the same optimal answer. We could have ones that are very different. We could have MAE and MSE returning the same model. That's also possible. Lots of examples on that, but you can imagine. One of the simplest things that you can think about also is if you can fit it exactly to a line, your loss function doesn't really matter as long as it's a good loss function. All of them will return that line. Anyway, so lastly, the number of learning steps, that's the number of times we iterate through SGD. I know we haven't talked about the algorithm that much, and you'll be doing a lot more of that algorithm soon. A model takes to reach an optimal solution is affected by its initial parameter values. True. False. All right. We have another true. So the counterexample that's really easy here is, imagine we have the optimal parameter values as our initialization. Then it takes 0 steps for it to reach the optimal solution. That's a very nice counterexample. There's also a very, very nice paper about how much initialization actually matters. And it's an interesting thing. I'm going to recommend it at some point. Yeah. By the way, you're going to have to scan it and upload it to Gradescope, just so you know. Cool. All right. Next. So now we're getting into some of the more serious questions. This is it does get incrementally harder as the questions go through. I don't know if you noticed that. Next question. Maybe exponentially. Imagine we have data that has very high and very low magnitude examples. So as I talked about before, we want to use those to get some proportional idea of difference. Instead of having these very big differences take over entirely what we care about, we want to have the proportion of the difference matter. This is imagining that we have some different idea of optimality. It's not the same we had when we had MAE, but we have some new ideas, so we have a new loss function. So, anyone have any ideas on how we do this? Instant hands, like it? Yeah.
Standardize the output you get and subtract it with standardized predictive and then do the MSE part.
Yeah, so standardizing the input and the output.
No,
Just the output?
Loss function, right? So just the output and prediction.
So standardize those over all of the predictions. That has a bit of a problem because then you need to do all of your predictions at once and standardize them.
No, standardizing would be calculated from the input, but would be standardized on the output.
So your idea doesn't work unless you do all the. I'll tell you. The idea is a nice idea. It's a nice idea, and it's something that we can do later. But for now, when we're doing one data point, one prediction, one update step, we actually don't have any way to standardize those output steps, and we can try any sort of standardization we want between them. We could say, how like between 0 and 1, but we still have the proportional difference, because when we standardize them, if we use some sort of like normal standardization, then we'd end up still with the big magnitude still being way bigger. We don't actually solve that problem. We solve a different problem, though. Yeah.
The loss function is the absolute value of y hat minus y over y hat plus y.
Yes, so it does work, but in a non-intuitive way, but yes, it does. So I'll tell you a little bit about, so here's a very simple way that you could go about doing this. We would just scale the magnitude of the loss so that, based on the output. So we scale the loss based on how big the output is. So we do something like this. We take the difference, square it, divided by the magnitude of our actual label squared. Squaring it there so that we don't actually have negative under there. You have to be careful of that. So if you just had over y, clever idea, but you need to make sure that it's always positive. Anyway, there's a lot of ideas of what you could do here. That one happens to be equivalent to this. This is, I think, slightly more intuitive, but they're both correct. Cool. Yeah. What if y is 0? Good point. you should have instead of this, you should have y plus epsilon squared, or y squared plus epsilon, or something like that. Or I guess it has to be inside that. So it has to be y plus epsilon squared, where epsilon is some small value, and then you'll never end up with a 0. Or you can, I guess no, you still won't, because you always have an epsilon term in it. So that does work. Yeah. Anyways.
Is this the only solution, or?
It's not the only solution. Yeah. Anyway, there is still a problem with what I said. I realize it could be equal to negative epsilon. Get over it. You can do this. All right. Cool. Good for calling me out, though, because I did actually say that we can't have one that divides by 0. It has to be defined everywhere. So good point. I'm violating my own thing. If you trust me, we can do something like this without actually physically dividing by y squared. Anyway, but something like that is what you want. You want to scale it by this. Anyway, so now we get to the fun one, the one that I'm sure everyone did not love, and that's sort of the point of the question, the computation graph. So I'll let you into a little secret so that you don't feel as bad about this being a really hard thing. This computation graph and doing the derivation of this problem was something that I had to do in 682. And it was difficult then, and it's difficult now. But I wanted to show you that it is approachable with the idea of computation graph, at least. And with a couple of clever ideas, we can actually get it manageable and actually be able to do it. Some of you picked up on some ideas that we could do there. I'm going to show you the very naive solution, which is just doing a computation graph the exact way I taught it to you, which is perfectly reasonable to do, because I haven't taught you anything else. But let's see what it looks like. So we have our x1 and our x2. Taking some data, we get them in. We're going to add them together. Then we're going to divide by n. Then we're going to take those values. So we're taking x minus this. I label it mu because that's the mean. We have each of them. We're doing it element-wise. And then we square them. And then we add those squares. And then we divide those by n, and that gives us our standard deviation. So now we've calculated both our mean and our standard deviation. Unfortunately, we are not done. That is just calculating the mean and standard deviation. We need to use them together now to get our final answer. So I'm going to now label this one, which I didn't label before, as m, which is mean zeroed input. So that is essentially the numerator. And then this term over there is a denominator. And all we have to do is divide them now. So we divide them together, and we get our output. So this is chaotic and awful and terrible, right? Yeah. This was a huge pain in making the slides, by the way, just so that I suffered with you. It is possible, though, that we can compartmentalize or make modules. So we have one module that would calculate mu, one module that taking in mu calculates sigma, and then another module that does the other operations we need. This is an idea that we're going to come back to later on when we are learning about PyTorch, which is based off of these modules. But essentially, you can think of the idea as taking these operations, and instead of doing these very basic operations, we replace them with more complicated operations, and then elsewhere draw the computation graph for that more complicated operation so we can simplify it. If you do that, this looks much neater, and it is much more beautiful, and you can actually use it, where this one is pretty hard to use. Anyway, so for the last question, the bonus question of actually using the computation graph, I don't want to actually go through the derivation because I think that will take a long time and won't be there'll be no point. So I'll tell you what I got. So I did, in fact, use a computation graph. I did, in fact, do the steps that we did. I wanted to see how difficult it would be to do that instead of just knowing the answer. And this is the answer I got. Now, I did do this very quickly before class instead of like checking it or anything like that. So it's possible this is wrong. So if you can prove that this is wrong and give me a correct answer, I'll give you extra credit. And as a bonus little thing to help you out, here is a link to someone doing this calculation and explaining it along the way. So if you'd like to get extra points, I'll upload the slides after. You can look at that link. You can see what I put, and you can see if you can prove me wrong. Anyway, that is going to be it for the answers. And now we get to submit the quizzes. So I want you to go through your answers and correct them. You don't need to draw the computation graph, but just sort of make note of what's wrong about yours or something like that. All right? And just take a couple minutes to do that. Yeah.
I got like an extremely similar answer. The only thing I did different was I did a summation thing.
Mm-hmm.
Should I scratch that off?
If you want to. If you think it's wrong.
Okay.
Yeah. Yeah. Also. All right, all right. I think that's enough there. We are going to be submitting it to Gradescope, and just to ease all of your minds, everyone's getting 100. You don't need to get anything correct on this quiz. It is just here to be a fun way to test what you know and to maybe take attendance. That's all it's here for. And right now, scan it with your phone and upload it to Gradescope. If for whatever reason you can't do that right now, the Gradescope is open until, I think, midnight, so you're able to do it until then. Okay. It doesn't matter. Yeah, it's for you. The going through and checking it is for you. It's not for me. I'm going to start lecturing again in like 2 minutes. If you haven't finished it by then, you can do it later. All right, all right. If you haven't been able to upload it yet, just do it after class. It's fine. It'll be open until, I think, midnight. If for whatever reason you can't upload it, email me, I guess. OK, now we're going to start something that I think is much more interesting, and we're actually starting to get to neural networks. It's happening. I promised at the beginning it's happening. So we have, just a quick reminder, we have this new model where we have some features in an input, some features in an output. And we know that regression is when we want to get some continuous output, and we want it to be similar to the real outputs that exist. And we know that we can use this model for it, where we just sum up the different x's times different y's. This is equivalent to this notation, which is just w transpose x, or w dot product x. They're exactly the same thing. You'll see that in the homework, plus b. And then we have classification, which is when we want to predict a discrete class, whether it's a cat or a dog, whether you passed or failed. We want discrete things, or it could be many different classes as well. So binary classification we talked about before, and we use this for it. So we just thresholded it and said if it's one side, it's a 1. If it's one the other, it's a 0. But this is only true for binary classification. So I'd like you, in your own free time or whatever, to think about how you might do multi-class. What if there's 5 classes? How do we actually go about doing this? It's not as easy as you might think. Cool. So this is where we're at. And now let's introduce a new notation. I'm sure you're all thrilled about it, but it's a good one. And we're making our way into neural networks now. So this is the sort of start of neural networks. I think people would call it the first neural network. Is if we are going to draw a sort of computation graph, a shorthand computation graph of this model that we're doing, we could draw something like this. We start with our 3 x's. This is a 3-feature example. And we have our 3 weights. And we're going to have them along the edges to mean multiplication. And then the nodes are going to be summation. And this would be, so we also have bias. Always forget about bias. Don't forget about bias. It is equal to this, which is just the summation that we had before. This is also the same as WTX plus B. So always remember that those two things are the same thing. And we also now have this idea, which I'm going to introduce right now kind of a nonlinearity. So what's a nonlinearity? It's some nonlinear function that we can perform on the model after it outputs. So in the case that we had before, this was the threshold. This was the greater than, this is the less than. That is actually a nonlinear function, where everything else on here is linear. So we could do that with some arbitrary function. We're going to come back to that idea later, but I just want to introduce now that it could be that. This model would mean either of those two things, and we could replace it with some other nonlinearity. We'll specify if we are later, but know that this notation can mean that. Now this right here is, it's the regression model that we've been using a whole bunch, but it has a name, has a neural network name. It's called a perceptron. A perceptron was the very first construct that we came up with, not we, but that people came up with to actually do this sort of machine learning. It's called perceptron because they initially used it for binary classification. It could perceive if something was happening or not. So called perceptron. They could have perceptron to tell whether there was a line in your image, was sort of the idea. It's based on some nice neuroscience. You can see why they maybe called it a neural network. We have the inputs are kind of like the dendrites that take in stuff, and then the synapse kind of does an operation, and then it outputs a 0 or a 1, kind of like a neuron. It's not a very good comparison, but that's what this is based off of, and that's why it's called a neural network. Anyway, so this is a very simple neural network, but there is some things to discuss about it. So firstly, so I guess the rest of the lecture, we're going to talk about something very interesting and fundamental that probably even those of you who know a decent amount about machine learning don't know about, which is a very interesting little proof that I'm going to show you. So let's say that we want to show, we have 2 features, x1 and x2, and we want the output of our network to give us x1 and x2. So here's our little model. It only has 2 features now, so it looks like this. And we have this truth table for that operation. I hope you're all comfortable with truth tables. They're not very important for the class, but They'll help you here. So that means, we only output a 1 when we're given 1 and 1. Okay, so this is our model, using, again, not the matrix notation, but it's equivalent to the matrix notation. Say that every time until people get that. So how would we set these parameters to make this be able to output correctly? Essentially, think of this as our data, and we're doing a classification on it. What parameters would work here? Any thoughts? Yeah. You can't? Yes, we can. Yeah.
You could set the W to go from 1, and then the B, make it like minus 1.9.
So we can, in fact, do 1, 1, and only minus 1. We actually only need to have put minus 1. We can see here that the only case where our output will be above 0 is when they're both 1. So our model is going to be, thresholding at 0. And if we have 1 and 1 multiplied together is 2, and multiplied and added together is 2, and then we can take a 1 bias off so that everything else will be 0 or below 0. So cool. Seems pretty straightforward. In fact, we could just use 1s and negative 1s. That seems pretty easy. Okay. Let's try a slightly different one of these functions. So this is XOR now. So again, we have our model, and we have a new truth table. This is our truth table now. So it's only, XOR is exclusive OR if you somehow don't know that. And that means that it will only return 1 if only one of the features is 1, and not if both are, or neither. So let's play the same game. Here's our model. How do we set the parameters? Anyone? Not you. Give it a little bit of think. Yeah.
1, 0, 0.
No. You know why I know it's not? Because we can't do it. So I was saying we could do this other truth table with the same amount of examples, same level of simplicity, but we can't do it. We can't do this one. Why not? Let's show you why. So let's plot it. So we have 0s and 1s as our features, and we will have 2 different classes, and they will look like this. This is XOR. So both 0, 0 and 1, 1 are both not, and then 1, 0 and 0, 1 are both yes. Does anyone immediately see the problem? Can't draw a dividing line. That's absolutely true. We can try. Put a line there. We're putting some of them on the right side, but one's on the wrong side. Put it there, same deal. And we actually know, in fact, that no line works. No line is able to successfully separate these. And to tell you a little bit of a history lesson, immediately after the perceptron came out, which is the precursor to neural networks, which I'm sure you're all well aware of and very interested in, someone wrote a paper. They have a name, I'm pretty sure. And they said, oh, look, the perceptron can't do XOR. It's garbage. And as a response to that, everyone told them that, oh, no, that does other stuff. No, they told them, you're absolutely right. Let's stop research on these perceptrons for 20 years and not talk about it at all. Let's go back to hand designing AIs. The person, by the way, who said that was the good idea was the US government. They shut down research on all perceptrons and all of this, this sort of AI that we're doing right now. So that's fun. But this isn't going to be the end of the story for us. So let's look at this example. I suppose I have animations, but it's OK. We don't need them. So what if we only have one single data point? Right? So we only have one input. This is just one of the things that's true from XOR. 0, 1, and it outputs 1. Well, we can give it these. So for all the zeros, we give it a -1 weight. All the ones, we give it a +1 weight, and then we bias it based on the number of ones that are in the correct answer. So we can do it with a single input, and in fact, I can tell you, we can do it with any single input. OK, maybe something's coming together here. Maybe. It is. I'll show you in a second. So let's use that idea to come up with something very interesting. Let's start with this one input. This is what we had before, right? Not a big deal. But now let's introduce a second one that's also one of the true examples from XOR. And we'll label them, the two perceptrons, Y1 and Y2. Right? And in fact, we're going to give them weight names. So this is a little bit of a Another notation thing here is that this weight is weight 1, 1. This means that it is the weight from input 1 to output 1. So it's going from x1 to y1, so we call it 1, 1. Likewise, for this one, we call it 2, 1 because it's going from 2 to 1. Anyway, so that's a notation. The reason it's labeled that way is it translates extremely nicely into matrix multiplication. But for now, just accept that that's how we label them. So we have this one, which is able to detect when this input occurs, which we know that is true for XOR. And we have one that can take this and give us a 1 for the other input. And it is, in fact, exclusive. It will only output a 1. I could prove it to you, but just trust me that it will only output a 1 when it sees that particular input. Anyone have any ideas of how we could use this? Yeah.
Another one connected to Y's now.
That's a very good idea. So let's see what happens with that idea. So we said that we're going to connect another one to those Y's. So in fact, we're going to create another perceptron that takes those Y's as inputs now and produces some output. And on that perceptron, we're going to give it weights of 1 and 1 and a bias of -1, doesn't matter. But what we find out is that this Y1 is detecting one positive case input. Y2 is detecting a different positive case input. So since we're covering all of the cases where XOR would output 1, we can essentially OR them together, which is just having two 1s together. And this neuron will behave exactly the same as XOR. So now we've seen that if we want to do a complicated problem like XOR, we can sort of put multiple perceptrons on top of each other. And this is an extremely interesting theorem and finding, is that because of how we formulated this, it's general enough that we can say that we can do this with any digital circuit at all, using just binary weights, using just this many layers, so just having a detector for every positive case, and one that ORs them all together, we can cover any digital circuit you could possibly think of. So this concept of stacking these perceptrons together, we call, very creatively, a multi-layer perceptron, or an MLP. An MLP is the basis of most modern neural networks. So hopefully I've convinced you that there's some reason that we use this kind of structure. It's a very interesting property. I'd also like to point out real quick that there is a problem with this. Let's imagine that we have something that has 80 input features, some digital circuit that has 80 input features, and all of them are positive, right? If we just imagine that. It returns 1 with anything, but we do it in this naive way. We'd end up with a number of perceptrons in this middle layer, is what we call it, of 2 to the 80th. That's unreasonable. We can't do that. So there has to be some way that we can do more complicated operations, because that's not actually that complicated of an operation when it comes to machine learning. It's just 80 dimensions. That's not actually that big. We do huge images. We do self-driving cars. So what we find is that not only can we combine neurons together that have multiple of these I call them pattern checkers, so multiple of these ones that check inputs that are positive, we can combine multiple of them together by using non-binary weights, by using integer weights. And then we can also increase the number of layers, and we find that that can reduce the number of neurons we need significantly. There's very interesting little tidbits. And then this is the advice part, so that is the end of the lecture, right? One thing that I want to say before we get to this,